Hello everyone, welcome to another Uiua video. Today we're looking at Advent of Code 2021, Day 14. I like this one a lot in Uiua. So what the problem is telling us to do is that we have this starting string and we have this list of rules to apply. And for every pair of letters in the starting string, we need to find its rule in this list. So for example, NN, the rule is here, and we need to insert a C between these n's. So we can see here the first step gets us this NCN that we would expect. In between the N and C, we insert a B, and in between the C and the B, we insert an H. So for part one, we need to do this 10 times, and we need to subtract the quantity of the least common letter from the most common letter. And that's as simple, yeah, and then for part two, it's a simple increase from 10 to 40. So the thing to notice here is that for part one, 10 steps, you could actually, I think, model this as a real string, and that would probably work, but it would probably be kind of slow. But for part two, there's no way that you can do 40 steps because the string itself would contain trillions and trillions of elements, and it would just be very slow to compute, or maybe even impossible. So what else can we do? So the first thing to notice is that the number of characters is all that we care about. So we don't actually care about the position of the letters within the string. We just need to know how many times each letter occurs. And the other thing to note is that we're always inserting in between letters, which means that there's no way to change the start and the end of the string. So it will always be N and B in this case for the test. So we can model this as an adjacency matrix. So these rules can tell us how we need to move at each step, and we'll encode that into an adjacency matrix using this list of sort of classifiers as the identifiers. Um, so let's get started because I think it'll be a bit easier to look at. So the first thing we need to do is separate this starting string from the rules so we can work on them separately. And we can use an unformat string for that. So what we'll do is this, and it will separate out the starting string and the rules. And this is basically breaking this on this double new line, which occurs here. So this is the unformat string behavior. And we actually want to look at the rules on top of the stack, so let's put it backwards here to flip the arguments. And then what we want to do is operate on each row or each line here. So let's start by just doing this kind of partition thing. We have this idiom PIBN and then the new line character, and that will get us this matrix of characters here. And let's just take the first line to start with. So we figure out what we want to do, and then we'll run this on each of the lines. So we can again use a format string here, or an unformat string, and we have these two characters that we care about, and then we need to delimit here. And this now gets us the first two characters and then this last character of the line. And what do we actually need to do? So we need this pair. This is our kind of lookup. And then we need the new pairs that will be created. So one will be HC, for example, and then the other one will be CN. So let's do that. So in order to operate on the same stack items with different functions, we use a fork. And by default, fork takes two functions, but if we give it a function pack, then we can give it three functions. So the first thing that we want to do is we want to join these first two elements. The second thing that we want to do is skip this first element and join B to H. So we'll use gap and then we'll do a back join. So discard the first argument, and backwards is call the function with the argument swap. So this will make sure it's B then H. And then the last thing we want to do is get C B. So for that we'll use reach, and reach is experimental, so let's enable that. And this is skipping the second argument, so that's how we can get the three things that we care about. So now we want to run this function on not only the first line, but on all the lines. So rather than identity as the function that we're giving to partition, we'll give it this function. And now we have all of our classifiers, all of the well, one of the next pair and the other of the next pair. So let's save this first classifier vector as C. So we'll just bind it here, and we can just label it. So now if we ever need this, we can just use C, and then we'll have access to it here. And the other thing that we need to do then now is index these new pairs into this original classifier vector, and that will let us start building up the adjacency matrix. So we want to apply index between stack item A and B and stack item A and C. So that pattern is done with sided both, and because we want to repeat A, let's say the first item on the stack, we point left, and we'll just use index here. And then we would like to put item 8 and item 2 in the first row of the adjacency matrix, and 3 and 6 into the second row, and so on. So we would like to enumerate this, and the idiom for that is unselect, enumerate the length of an array, as it says. So now we have this, and we would again like to join these or couple these, 0 and 8 and 0 and 2. So it's the same sided both pattern again. So we can do that, and we'll do a couple with rows so that it applies to each of the rows. And this gets us what we are looking for. And so how can we go from this, and we can actually join these together. So how can we go from this list of indices to the actual adjacency matrix? Well, I'm very happy to say that it's as simple as this unware function. So it converts the list of indices into a mask, which is exactly what we want. So we have the ones at the position that we had, and I can bring back the original indices. 0, 8 is here, and 0, 2 is here, and this is the 1, 3 that we had, and so on. So this is our adjacency matrix, and we can bind this to M, and we can label it as well as adjacency matrix. So now we have our adjacency matrix, we have our classification vector, and now we have our starting string. And how can we sort of iterate with this starting string and this adjacency matrix to model the behavior of this pair insertion? Well, we can start by converting this string into the correct sort of vector format. So what we would like to do is look up each of these pairs in this classification vector. So let's start by getting the pairs, which in Uiua is done by using stencil with couple. So this will get us our pairs. And then we would like to grab or index here. So we'll use index. This gets us the indices that should be marked as 1, and we'll again use unware. So this gets us our 7, 9, and 2 marked as 1. And this is almost what we need. The only thing that's missing is the rest of the zeros that would be out here, based on the classification vector. So after element 9, wherever it is, somewhere here, these are all zeros implicitly, but we would like it to be explicit. So what we can do is, let's step back a moment, and rather than only indexing, we can do two operations with fork. So we want to still have that indexing, but we also want to take the length of this vector. And now we have what we need, because we can use unware, and then we can use back take. So basically saying take 16 elements from this vector. And this will error because there's not actually 16, but if we give it a fill value, and in particular fill value of 0, then this gets us what we're looking for. So now we have our starting vector. This is the encoding of NNCB, and we have our adjacency matrix. So how do we actually iterate? We need to use a matrix vector product. So basically we want to multiply each row of this matrix by each row of this vector, or each element of this vector. So just to maybe show that visually, I could do something like this. So we basically want to apply multiplication between 0 and all of these elements, 0 and all of these elements, and that's basically saying that we don't have any of these items, right? So we don't have any CHs, so we shouldn't add any of the pairs that are generated by a CH. And same thing for HH, we don't have any of those. But here we do have a CB coming from the starting string. So we should add a pair of, CH, this first column is a 1, and this fifth column, 0, 1, 2, 3, 4, is also here, HB. So we should add an instance of the pairs coming from this row. And we do that for all of the instances of pairs that we have and don't have. So how can we do that? It's actually really nice in Uiua because it's literally just multiplication. So Uiua has what's called leading axis agreement. So because the first axis of both arrays has the same size, in this case 16, we can simply multiply them together. And after this, we want to add down the columns so that we gather all the instances of each pair. And this is one step of our iteration. So we can do this as many times as we need, basically. We can put the adjacency matrix again on the stack, we can multiply, and we can add down the columns. And we're iterating twice now. So let's use a repeat for this, which will let us repeat this 10 times. So now we know after 10 steps, we will have 21 instances of CH, 32 of HH, and so on. This is pretty close to what we need, but we actually don't need the occurrences of the pairs, we need the occurrences of each letter. So how can we do that conversion? So the important thing to note here is that every pair is causing letters to be double counted, because every second letter in the pair is the first letter of another pair. And that's the case for everything except for the last letter. So this B is not the first letter of another pair, but for the most part, with the exception of the last letter, we can simply use the first letter of the pair to indicate which letter we're counting that pair for. So let's grab our classification vector, and we only want the first of each row, so let's use rows first. And now we want to be able to group these. So we want to group, okay, there's 21 C's, there's 115 of this C, and so on. There's other C's here. So we want to group these all together. And we can do that by turning them into their position in the alphabet. So if we subtract capital A, then C will be 2. So it's index position 2 in the alphabet, and so on. And then we can use group, so it will group based on these indices, and it will apply a function to the items it grabs from the second item on the stack. And in this case, what we want to do is we want to add. So maybe I can start by just boxing, let's say. So the second 0, 1, 2, right? The second box here is the C's, and there are 21, 115, and so on, and we want to add these together. So rather than boxing, let's use a plus reduction, and now we have what we're looking for. Well, almost, right? So the B's here, 1748, this is almost right, but we know that we're missing this last B that's at the end of the string. So let's go back to here. Before we turn this into the starting vector, we just would like to keep this last letter on the stack. So we can use on last. So last will get us the last row, which will be the B, and on will call the function but keep the first arguments on top of the output. So now we have our B, and we still have our starting string, so we can do all of this again, or uncomment it. And now what we'd like to do is figure out the index, so we'll again subtract A, so now we know this is at index 1, and we need to add 1 to index 1. So we can do that by using under. And under will apply a transformation, then do an operation, and then reverse that transformation. So in this case, the transformation that we want is pulling out or picking out this element of the vector. So we'll use back pick. So we'll pick with this from this. And the operation that we want is increment. So there we go. Now the first position has been incremented by 1. And this is now what we need to actually give us the answer. We can remove the zeros, so we'll use keep by sign. So the sign of a number, in this case positive numbers, is 1 and 0 is 0, so we can use this as a binary mask for keep. And then we want to pull out the maximum and the minimum values, and then we simply want to subtract them. So this is our answer for part 1, and this is our answer for part 2. And we can turn this into a function really easily by just wrapping this whole thing. And now we can do something like P1 is solve with 10, and P2 is solve with, not 20, 40. And I can put them both here, and there we go. These are our answers to part 1 and part 2, and they run almost instantaneously. Also, if you were to put the real input in, the full size one, it will also run basically instantaneously, because it's just multiplication and addition, and that's very fast. So yeah, I think this is really cool. I like getting to build these adjacency matrices using unware. I think that's very powerful. The matrix vector product with the leading axis agreement is also very powerful. How easy it is to do these kinds of operations that could be more complicated, or at least require more ceremony in other languages. And overall, I think it's just a really nice problem that makes you think creatively about how you can model this kind of exponential growth as a simple adjacency matrix. So I hope that was interesting. Hope you learned something. And I really appreciate you watching. I'll see you in the next one.